Well, I'm Dr. Alva Dusatz, founder and chair of the International Society of Unified Science. This is part 5 of my paper, Theory of Unit Space-Time and Displacements of Unit Space-Time, Material and Cosmic Photons, Subatoms, and Atoms. On page 70, section F, Cosmic Ray Decay and Material Atom Building. 1. Original rays. The original rays come from the cosmic sector, which is the inverse sector in the reciprocal system, by means of gigantic cosmic galactic explosions, commonly observed as gamma ray bursts. The cosmic atoms are ejected above the inverse speed of light, that is 1 to 3 c sub c, which means that they're at or below the speed of light here, c sub m, in our usual one dimension of observation. The cosmic sector is not localized in space, so the distribution of the cosmic rays in the material sector is isotropic as observed. All of the cosmic atoms are fully ionized with negative charges. The abundance of the various elements is not too different from that of late-stage material matter, as determined by the number of charges. But there's the usual cutoff above iron. The charges are transferred to massless, chargeless electrons when the original rays strike the top of the Earth's atmosphere. 2. Primary rays and secondary rays. These mostly consist of C hydrogen, C helium, and C protons. Other subatomic particles are absent because they cannot be accelerated above C, except for those charged electrons created in the collision processes in the atmosphere. Apparently, the cosmic protons and cosmic hydrogen atoms, assuming they do not have gravitational charges, simply invert their rotations to convert to their material equivalents, because 1 U of cosmic mass equals 1 U of material mass, and 2 U of cosmic mass equals 2 U of material mass. Cosmic atoms above C krypton fragment to C krypton or below. These then shed material mass, that is, they gain cosmic mass, until they reach C krypton, at which point the rotations can invert to form 2 massless neutrons. Starting with cosmic deuterium with 2 material gravitational charges and reading down to C krypton with 0 material gravitational charges, Table 6 above, that is in the previous part of this paper, gives the normal decay sequence. Of course, any cosmic element in between is possible depending on the circumstances. Also, mass and energy conservation must be observed in these transformations. So this equation here, C krypton goes to 2 massless neutrons. You can see it there. Recall that 3 magnetic displacement units in space, and by the way, these are double rotations because we're dealing with atoms, equal 1 magnetic displacement unit in time, that is 4 minus 3 equals 1. See reference 1, second edition, page 187. The massless neutrons then undergo further transformations in our sector. 3. Massless neutron transformations, and here I'm going to use effective displacements. So massless M neutron plus the massless M proton, or excuse me, minus the massless M positron equals an M neutrino. Massless M neutron plus a massless electron equals a material neutrino. And a massless M neutron plus an M neutrino plus unit mass equals a proton, or a material proton. The unit momentum of the massless M neutron, T squared over S squared in space-time dimensions, provides the energy T over S, which is converted to mass, T cubed over S cubed, when the particle comes to rest in a gravitationally balanced system. Recall that the massless M neutron and the M neutrino have potential mass. That is, they don't have actual mass, but they do have potential mass. The sum is 0.000578552 plus 1.0066507 U equals 1.007229226U, which is the mass of the chargeless proton. Okay, so what we've done here is we've shown that the cosmic matter eventually converts to massless material neutrons, which then convert eventually into protons. Now, the chargeless proton on section 4 in a hydrogen isotope 1, the chargeless proton created above combines with a material neutrino to create the first isotope of hydrogen. And there you can see the displacements. Notice that hydrogen isotope 1 is actually an intermediate particles because the displacements of the two rotational systems are not identical. And then finally, 5, hydrogen isotope 2, which is deuterium. Two chargeless protons can combine to form deuterium, which is D or H2. And this is the first real atom of the material periodic table because both rotational systems have the same rotational displacements. So we can now simplify the notation to be just 2-1-1. However, gravitation is reversed within the time region, becoming a force of repulsion, so that a direct combination of two protons is rather improbable, even if they are uncharged. Atom building beyond H1. Neutrinos can acquire magnetic charges by interaction with matter or photons. As stated above in the section on isotopes, the magnetic charge of the neutrino can induce a gravitational charge in an associated atom, adding 1 AMU to the total atomic weight. If this puts the isotopic weight of the atom outside the zone of stability, some of the vibrational mass is converted to rotational mass, thus moving the atom to a higher position in the periodic table. This is, in a sense, somewhat like reverse beta radioactivity. So equations 49 give the basic equations here. With 2Z plus G sub m, which is the gravitational or isotopic charge, plus 2 times nu EM, which means it's a magnetically charged neutrino, goes to 2Z plus Gm plus 2. And then we have 2Z plus Gm plus 2 goes to 2 times Z plus 1 plus G sub m. And so overall we go from an atom of atomic number Z and atomic mass A to an atom with atomic number Z plus 1 and atomic mass A plus 2. And again, mu sub em is the magnetically charged neutrino. 7. Speed and location of atom building. In reference to pages 282-283, Larson says, atom building in intergalactic space is slow because of the low density of matter, but the amount of time spent in this state is so long that there is sufficient opportunity for the production of a finite quantity of all of the 117 possible elements, plus the unstable 118, in proportions determined by the relative probabilities. After this initial period, the existing matter is increasingly concentrated into larger aggregates. This speeds up the atom building, but meanwhile there are processes in operation in the interior of stars that destroy some of the heavier elements. The atom building takes place everywhere because the cosmic rays are everywhere. The heavy elements are not created by supernovae. The outward moving debris consists mostly of lighter elements. And so incidentally, it's not dark matter between galaxies, it's the non-luminous matter which is created from the incoming cosmic rays. Okay, number 8, abundance of elements and even odd atomic numbers. As Larson points out, reference to page 285, quote, evidently a single addition to the atomic rotation introduces a degree of asymmetry that decreases stability, as the even-numbered elements are generally more abundant than the odd-numbered ones. For instance, the 10 most abundant elements beyond hydrogen in the Earth's crust include 7 even-numbered elements and only 3 with odd atomic numbers. The zone of isotopic stability is likewise wider in the even-numbered than in the odd-numbered elements, as would be expected if they are inherently more stable. Many of the odd-numbered group have only one stable isotope, and there are 5 within the 117 element range of the terrestrial environment that have no stable element at all in that environment. On the other hand, no even-numbered element other than beryllium has less than 2 stable isotopes. Section G, mass gravitation and inertia. The rotational spins of each atom and subatom with mass are the cause of that mass and its inertia. No Higgs bosons here. The resultant translational motion is in opposition to the space-time progression, and this causes the atoms and subatoms with mass to move inward toward each other outside unit space. This is gravitation. There are no gravitational waves, gravitons, or Higgs bosons. See reference 17 for a detailed treatment of the interplay between gravitation and the space-time progression. H. Matter properties. The properties of matter depend on the rotational displacements of the atoms and numbers derived from these displacements, not from, quote, wave functions. For an isotope like U-238, the quantum mechanics theorist has to work with 92 protons, 92 electrons, and 146 neutrons, each of which has the, quote, wave function. In contrast, the reciprocal system theorist works with the rotational displacements 4-4-6 plus 54 gravitational charges. This represents a vast reduction of complexity, and therefore makes possible the ab initio calculation of all the properties of matter. No longer can a theorist say that although he can solve the problem, quote, in principle, he cannot, quote, in fact, because of the mathematical complexity. In the author's current series of papers, such as references 9 through 18, many properties have been calculated and the resultant equations put into the reciprocal system database, which, by the way, the Microcosmos module is now available. A number of chapters in Larson's works, reference 2 and reference 1 second edition, are sufficiently detailed so that the present author could directly code the properties into the database. These chapters include the following: basic properties of matter, that is solid cohesion, interatomic distances, distances in compounds, compressibility, heat, specific heat patterns, temperature relations, and thermal expansion. And nothing but motion, simple compounds, complex compounds, chain compounds, and ring compounds. The other chapters dealing with electric and magnetic phenomena, particle physics, radioactivity, matter states, etc., have been translated into the language of mathematical physics in the author's papers, including this one, making it easier to code programs in the database. 5. Atomic transformation and stellar energy generation. Concepts. The most important atomic transformation in the universe is that which generates stellar energy. The reciprocal system rejects the so-called standard solar model. See reference 1 through reference 10. Larson explains the reciprocal system alternative as follows, reference 3, page 41. From theoretical considerations, we deduce that at some point after the interior of a contracting cloud of dust and gas has been raised to a high temperature by gravitational energy, a relatively rapid rise in the temperature of the entire aggregate occurs when the destructive limit of the heaviest element present is reached in the central regions, and conversion of mass to energy begins. As explained in Volume 2, both the thermal energy of the matter in the star and its ionization energy are space displacements, and when the total of these space displacements reaches equality with one of the rotational time displacements of an atom, the opposite displacements neutralize each other, and the rotation reverts to the linear basis. In other words, both the ionization and a portion of the matter of the atoms are converted into kinetic energy. Inasmuch as all atoms are fully ionized before the temperature limit is reached, and the heavier atoms are capable of acquiring a greater degree of ionization than the lighter ones, the amount of thermal energy required to bring the total space displacement up to the limit is less for the heavier elements. The Limiting temperature is therefore inversely related to atomic mass. But translating these concepts into mathematical physics has not, unfortunately, proven to be easy. Reference 60 and reference 61 give the previous attempts, which concluded that the thermal destructive temperatures are in the range of 10 to the 13th to 10 to the 14th Kelvin, which is patently ludicrous. Transforming potential gravitational energy at the rim of a star to kinetic energy at the core of a star brings the temperature of a heavy element up to approximately 1 billion Kelvin. The thermal destructive limit can therefore not be much higher than this. Also, the relevant natural temperature unit to use is not the usual time-space gas temperature, which is 7.2042 times 10 to the 12th Kelvin, but rather the vapor and condensed gas temperature unit, 3.5978 times 10 to the 9th Kelvin. Stars contain condensed gas, not perfect gas. See reference 2, page 60, reference 3, page 107. Calculation of destructive temperature. A magnetic rotational displacement, which is two-dimensional, n, is equivalent to 2 times n squared electric rotational displacements, which are one-dimensional. Translating the above concepts to mathematical physics, we obtain the relationship between these rotational displacements and the destructive thermal limit. So 2n squared equals z, which is the atomic number, times the quantity 1 minus t sub v sub u divided by t destructive, plus E sub I, which is the ionization energy, divided by 2 times the conversion factor from AMU to U and conversion factor of U to MeV. So again, T sub Vu is the natural temperature unit for vapor condensed gas state. E sub I is the total ionization energy of the element in MeV, and Z is the atomic number. So solving for T destructive, we get equation 50b, which you can see right there. The value of NTUs is the principal value minus 1 because the first displacement is ineffective, or the secondary value, whichever is greater. Neglecting E sub I for the moment, we can plot the destructive temperature as a function of atomic number as follows. And there's a MathCAD program there. And there's figure 1, destructive thermal limit versus atomic number. What's interesting about this graph is that for elements from z equals 69 down to z equals 66, the destructive limit is lower than that for z equals 117. From z equals 66 downward and z equals 117 downward, both curve segments are in play. So let's do an example calculation. We'll use thorium for this example. Thorium's atomic number is 90. The magnetic rotational displacement is 4. E sub I for thorium is 0.68836 MeV from the Reciprocal System database. So we calculate the destructive limit for thorium is 5.582758 times 10 to the 9th. Leaving out the ionization energy, which is actually kind of small, we get the destructive limit as being 5.582793 times 10 to the 9th Kelvin. Including ionization lowers the destructive thermal limit by just a little bit. Gravitational energy at the rim of the star and kinetic energy at the core of the star. Continuing with thorium, but without isotopic charges, let's consider what happens as the atom of this element makes its way from the rim of the star to the core. And by the way, we're observing gravitational segregation here. The heaviest elements will settle in the core, and the lighter elements will be on the surface of the star. Nothing unusual here. By the first law of thermodynamics, the gravitational potential energy of this atom at the rim, neglecting the small kinetic energy, changes to kinetic energy at the core, and these values must be equal. And there I show the mass of the thorium atom in MeV, and then the mass in kilograms. and then we set the kinetic energy to the gravitational potential energy, equation 51a, where the relativistic form for the kinetic energy is on the left-hand side because velocity can be quite high, and where the current, mass, and radius of our sun is used on the right-hand side for convenience. So we're taking our own sun as this example here. So solving for the velocity, we get 0.00206 C. The total energy is independent of the mass, although only the heavier atoms, those of iron and above, will make it to the core of the star. The kinetic energy is 0.355794 MeV, which is the same order of magnitude as the ionization energy. Incidentally, the energy of our ionization does not come from gravitational energy. If it did, there would be nothing left for the kinetic energy. So the ionization energy for the atom under consideration must come from the net energy generated when another atom reaches the destructive limit. The atoms in the immediate vicinity must all become fully ionized if they were not originally. And there's something else. The atom here is not going to be losing energy by radiation because it's going to be absorbing and emitting the high energy photons coming from the core. So the gravitational potential energy gets completely converted into kinetic energy, which then leads to the temperature at the core of the star. The temperature of the atom in the core of the star is calculated based on an assumed thermal distribution of velocities. One would use Maxwell's distribution for a perfect gas, but we're dealing with a condensed gas or vapor here. Unfortunately, neither conventional theory nor the reciprocal system has a suitable distribution for the state of matter, although hypothetically we could throw in a compressibility factor. It's going to have to be worked on later. But therefore, we will have to use Maxwell's distribution as an approximation. Pending further theoretical work, Maxwell's equation is given here in equation 53a. And incidentally, there has not always been agreement as to how to apply the Lorentz factor on the right-hand side. It's reference 62. So now we solve for the temperature, T, and we get 2.75233 times 10 to the 9th Kelvin. The ratio of this temperature to that of the destructive thermal limit is about 0.493. So the gravitational energy provides only about half the energy necessary. But the velocity calculated above is the root mean square velocity. Some atoms will have a higher velocity, and thus they will reach the burning temperature. We can calculate the fraction of atoms reaching the higher velocity as follows, and you can see their equation 54a. And so we get velocity, the destructive velocity is 9.660338 times 10 to the 5th meters per second, which is 0.003222 C. The fraction NSB of atoms at this velocity after traveling to the core is, and based on reference to on page 261, where the average temperature is still T, we get that this factor U is 1.915167, and that gives the fraction as being 0.061933. So over 6% have this velocity burning commence for those atoms. Okay, now we're on stellar energy generation. The amount of energy so generated is quite astounding compared with the supposed conventional hydrogen to helium process. When thorium loses 32 electric rotational displacements, it becomes cerium. Presumably, cerium is fully ionized upon conversion. And so from the reciprocal system database, the energy of ionization of cerium is 0.227387113 MeV. The stellar energy generation is going to be 32 times 2 times the conversion factor from AMU to U times the conversion factor of U to MeV plus the difference in ionization energies between thorium and cerium. And we finally calculate, when there are no isotopes here, 5.959714 times 10 to the 4th MeV. This is the situation where the magnetic ionization level is 0, that is, G equals 0 for both of the atoms. But suppose the atomic conversion takes place in an environment where the magnetic ionization level is 1, as in our present-day solar system. So G is not equal to 0. The difference in G between the two atoms must also be converted to energy. In the thorium to cerium case, we have G thorium equals 52 and G cerium equals 22. So then we calculate that the energy generated is 8.75330 times 10 to the 4th MeV. Where we're using isotopes here, it's mid-range and the magnetic ionization level is 1. So even though heavy atoms are very rare, the amount of energy generated totally compensates. Section F, stellar reaction rate. According to Professor Lang, reference 39, page 236, the luminosity of the Sun is 2.38943 times 10 to the 39th MeV per second. His hydrogen to helium calculation yields per reaction 26.2164 MeV. Therefore, the number of reactions per second for the conventional theory is 9.114286 times 10 to the 37th reactions per second. For the reciprocal system, using the thorium to cerium calculation above, as an example or average, we have 2.729754 times 10 to the 34th reactions per second. The ratio of the number of reacting atoms of thorium to that of hydrogen then needs to be at least 2.995028 times 10 to the minus 4th. Heavy elements may be rare, but obviously there is sufficient number to produce calculated stellar energy generation. Professor Lang, reference 39, page 164, says, quote, all of the heavy elements comprise only 0.1%. But this is more than sufficient. Reciprocal system calculations given above apply to all main sequence stars and all stars approaching the main sequence. Of course, substituting the appropriate stellar mass, radius, luminosity, and atomic species. Note, the number of neutrinos generated in the reciprocal system reaction to the Sun is not necessarily 30 times n reaction per second. It could be considerably higher simply due to the huge energy generated. The conventional calculation says that there are 2 electron neutrinos created per reaction, yielding a flux of 1.822857 times 10 to the 38th neutrinos per second from the Sun. To get the same number from the reciprocal system, there would have to be 6,678 neutrinos per reaction. Keep in mind that the ratio is, okay, so we had that. It's E stellar energy generation divided by E conversion factor of stellar energy generation equals 3338.867121. The number assumed yellow photons gated per second equated energy to the total energy of the initial gamma and X-ray photons would be nu sub yellow is 4.1 times 10 to the 14 cycles per second. And so that would give us 5.156891 times 10 to the 10 photons. So a conversion of just a few thousand of these to neutrinos is certainly probable. The conclusion of the paper before we get to the appendices. This paper has applied the reciprocal system to numerous properties of space-time, photons, subatoms, and atoms. Included are the properties of multidimensional motion, space-time geometry, light deflection, advance of the perihelion of Mercury, redshift of light, Planck's constant, the Stefan-Boltzmann constant, the origin of the 21.1 centimeter radio waves, Doppler shift equations, polarized light, massive subatoms, and cosmic atoms, the true identity of the so-called bosons, the cosmic rate decay sequence, atom building in our sector, the thermal destructive limit of the elements, and stellar energy generation. All calculations are consistent with experimental and observational data. Acknowledgements. Funding for this work came from Transpower Corporation, not the government. Of course, great thanks go to Dewey B. Larson, who served as my theoretical physics mentor from 1965 until his death in 1990. He was by far the most intelligent and most logical of any individual I've ever known. That concludes part 5 of this paper. Stay tuned for part 6, where I will go over the appendices, in particular the periodic tables.